Okay, so as I was saying, the last time we were here, we were talking about how to determine the number of significant figures in a given measured value. And I won't go through that again because we covered it at the end of last class. But most of the rules have to do with zeros in a particular situation. So now what we're going to do today to kick things off, minimize that. What we're going to do today to kick things off is to talk about how do we deal with significant figures when we're doing mathematical operations. And again, this is something that you guys should have done in your introductory or high school chemistry. One key point you need to keep in mind when it comes to mathematical operations and significant figures, and that is that a calculated quantity can be no more precise than the least precise data used in the calculation. And the reported value that results from that calculation should reflect this fact. All right, so basically what we're saying is that if you're doing a series of mathematical operations, it doesn't matter what it is, addition, subtraction, multiplication, or division, you need to round off appropriately to reflect in the final answer the number of significant figures or decimal places appropriately. And that will be dependent on which of the values involved will have the lowest number of sig figs or lowest number of decimal places. And also it's dependent on the type of mathematical operations involved and the sequencing of the mathematical operations. So that's what we're gonna look at now. An analogy that can be used to further explain and understand this is that a chain is only as strong as its weakest link. All right, so basically the weakest link would be, of course, the one with the lowest number of significant figures or the lowest number of decimal places based on the mathematical operations, as we're going to see shortly. So there are two separate rules when it comes to dealing with significant figures and mathematical operations. There's one rule which applies to the operations of multiplication and division, and then there's another rule which applies to addition and subtraction. So what you see on the screen here is basically the rule that operates or that applies when it comes to multiplication and division as mathematical operations, right? And this rule says that the reported results should have no more significant figures than the factor with the fewest significant figures, all right? So basically what that means is that if you're multiplying, for example, these two numbers, 1.827 meters by 0.762 meters, and you do your thing on your calculator and you press the equal sign, then what will come up on the calculator display is going to be this, 1.392174. Now, according to this rule, that final answer must be rounded off to the lowest number of significant figures of the numbers involved in the calculation. So for this number, we have 4 significant figures. For this number, we have 3 significant figures. So according to this rule, we need to round this off to 3 significant figures, which would be 1.39, all right? So basically, this is the answer, 1.39. And please note that also as a part of the, also as a part of the final answer is the unit meter squared, because you multiply meters by meters. So this underscores what I was saying last class. Whenever you're doing any calculation, make sure that the units are part of the process, right? Don't just drop the units, because any measured value must have units associated with the quantitative part or the numerical part, all right? So that's what you do for multiplication and division. This is a multiplication example, but you do the same thing if you were dividing these two numbers. Again, you'd round off to 3 significant figures, all right? Okay, so that's multiplication and division. In the case of addition and subtraction, according to the rules, the reported results should have the same number of decimal places as the number with the fewest decimal places. So for example, if you're adding these numbers here, 49.146 plus 72.13, and then you're minusing after that 9.1434. If you punch those numbers into your calculator, this is what will appear on your display. But according to this rule, your final answer must be rounded off to the fewest number of decimal places. So that means you'd have to round off to where this 3 is. So therefore, the final answer, which would be rounded off correctly, would be 112.13, all right? Okay, so that's basically how you do with addition, subtraction on the one hand, and then multiplication, division on the other hand. So this begs the question, how do you deal with a combination of such mathematical operations? So I'm just going to create an arbitrary example here. I don't know what the answer is, but I'll show you how to get to it. Okay, so let's say you were given this problem. 35.796 minus 2.13, and then you divide this by, let's say you divide this by, I just want to make up a number here, 4.5. Okay, so let's work with this. Now, in this case, you'd have to do things in parts, right? Because you have two different types of operations. You have the minus or subtraction operation, which is up here, which serves as the numerator in this fraction. And then you have to divide by this, okay, what's going on here? Why is this not? Okay, I don't know what's going on here. Oh, okay. And then you have this part here, which you have to divide whatever the result that you work out up top here, you have to divide by 4.5, right? So this is how you do this. You're going to do this part here first, the numerator. So let me get my calculator out and let me do it here. So according to this, 35.796 minus 2.13. Okay, so according to my calculation, the top part works out to be, I'm just going to write it above here. The top part works out to be 33.666, all right? So that's what you get when you work out the top part. But because you're doing subtraction, according to the rules, you have to round off to the lowest number of decimal places of the numbers involved in the calculation. So here you have 3 decimal places, here you have 2, which means that you need to round this number here to 33.66, all right? Then you divide by 4.5. So in this case here, you're going to be doing a division, right? And let me do that division, 33.66 divided by 4.5. So according to my calculations, this works out to be 7.48, right? However, because you're doing division, you have to round off according to the lowest number of the significant figures involved here and involved here. Here you have 4 sig figs. Here you have 2 sig figs. So therefore your final answer must be rounded off to 2 sig figs, which means that this becomes 7.5, all right? So that's how you deal with a situation where you have different types of operations involved. Basically you have to do one type of operation first, round off appropriately, and then do the next type of operation next, and round off appropriately, and so on and so forth, depending on the problem that you're given. Okay, any questions about this? Any questions? Any questions? No questions? Okay, so let's do an example. And this time I want to hear your input. So let's say you're given 2.56 plus 7.48 9 divided by 3.79 subtracting 2.5. Okay, let's work with this. All right, folks. So what would be the very first step in this process?
Add 2.56 and 7.489.
Okay, so if you add let me do this here. 2.56 plus 7.489, the answer I got here is 10.049. What next would you do?
Subtract your second equation.
Well, it's not subtract, it's divided by.
So you would divide, then subtract.
I'm sorry, I misunderstand. You're talking about doing this operation here, right?
Yeah, do that operation first.
Okay, so 3.79 minus 2.5. Okay, so when I did that, the answer I got for this part is 1.29. Okay, so what next would you do?
You need to make it the right number of sig figs. So like for the
Oh.
10.0, it only needs to be 3 sig figs.
No, that's not correct. No, that's not correct. You need to round off, but you're not rounding off according to the lowest number of sig figs. You're rounding off according to what?
The 0.049,
Yeah, but you're going to round it off to
10.1.
nope.
The lowest amount of decimals.
Exactly, round off to the lowest number of decimal places, because remember, here you're doing addition. Whoops, why is this thing not working? Okay, here you're doing addition. Addition, all right? And according to the rules, if you're adding or subtracting, then you round off to the lowest number of decimal places. So how many decimal places you need to round this number off to?
2.
Nope. Well, yes, I'm sorry, you're right, 2. You're correct. I don't know what's wrong with me this morning. You're absolutely right. So what would be the result of rounding off that to 2 decimal places?
10.05.
10.05, right? And then for the next number here, what do we do with this number?
You round it to 1 decimal.
1 decimal place.
So it's 1.3.
1.3. Okay, so when you divide this by this, let me do this on my calculator here, 10.05 divided by 1.3. Okay, so the answer I got here is a very long number, 7.730769,231. So that's what I got when I do that calculation in my calculator. So what do I do with this number?
You make it 2 sig figs.
Exactly, round off to 2 sig figs, because between this number and this number, this has the lowest number of sig figs here. So therefore, this is 2 sig figs, which means that you have to round off this answer to 2 sig figs, which becomes 7.7. All right? And that's basically how you're going to do all calculations in this course, right? You have to round off to either the correct number of sig figs or the correct number of decimal places, depending on the type of calculation, okay? Any questions about this? Any questions? Any questions?
Oh,
Okay, let's see. There's something I think I should mention and it completely escapes my mind, and I'm sure it's going to come to me later on. Oh, now I remember. Let me get rid of this here. Now, if you recall, I talked about there are 2 types of numbers that you will be using in any calculation. You have the exact numbers. Let me just refresh your memory a bit. Exact numbers, which are the numbers obtained by definition or counting. And then you have measured numbers, which are, of course, obtained by measurement. All right. Now, what if you have a sort of problem where you have both exact numbers and measured numbers? So, for example, let's say you have, and this is a problem again I'm making completely, from my head. Let's say you have 5 pencils, each of length 5.5 centimeters. All right. What is the total length if the pencils are placed end to end of each other? All right. Relatively simple problem, right? You have 5 pencils, each of them has a length of 5.5 centimeters, and you put each of them head end to end, and you want to find the total length of that arrangement, right? So we all know how to calculate it. Basically, we take the 5, which represents the number of pencils, times the length of each pencil, right? So let's see what that gives. 5 times 5.5. Okay, so according to my calculation, this works out to be equal to 27.5 centimeters, all right? However, we have to take into account the fact that this number here is a measured number, right? The 5.5 is a measured number, while this number here is a number obtained by counting, so therefore it's an exact number, all right? So according to what we learned, whenever you're doing any multiplication, you have to make sure that your final answer is rounded off to the lowest number of significant figures. So the question now becomes, what are the number of significant figures involved in each of these numbers? For this one, it's obvious. The answer is 2 significant figures, right? And when it comes to any measured number, the number of significant figures are infinite. So this number here has an infinite number of significant figures, all right? So therefore, since 2 is less than infinity, that means that we have to round off this final answer to 2 significant figures, which becomes 28 centimeters. So that would be the final answer in that case, all right? So I'm just giving you these examples so that you know what to do when you're faced with a problem. And the key thing I would say when it comes to doing these problems is that, one, you have to identify which numbers are significant, or I should say, which numbers are measured values and which numbers are not measured values, but are exact values, right? So you have to read the question and interpret it correctly in terms of the numbers involved. The other thing too you have to recognize is the rules for multiplication and division as opposed to addition and subtraction. So those are the things you have to keep in mind when you're doing these problems, because once you know the rules for rounding off, then you would successfully round off your answers to the correct number of significant figures and or decimal places. Okay, any questions about what I've just discussed? Any questions?
No.
Okay, good. All right, so let me get out of this here and go back to, okay, so what we're going to talk about basically, again, this is something you should have learned in your previous chemistry experience. How do we solve problems, especially problems when it comes to conversion from one unit to the next, all right? So, for example, we know that there are some unit equivalents where we can write down the relationship between one unit or another. So, for example, the relationship between the inch unit and the centimeter unit is shown here. 1 inch is equal to 2.54 centimeters, all right? So that's basically established, and therefore you can utilize this relationship to convert a value from inches to centimeters or vice versa. And how we do that? Then we do that by using what we call conversion factors. Now, before we get to that type of exercise, I just want to show you this list here. This is a short list of various unit relationships, which you don't need to memorize, of course, because I have provided it for you in Canvas in the file that is located in the tables folder, right? So the that document or that file or that document has a more expansive list of these relationships, right? Now, the conversion factor basically is a fractional expression of these relationships, these equivalent relationships. So, for example, if you look at the relationship between the inch unit and the centimeter unit, you see that it can be expressed as either 1 inch divided by 2.54 centimeters or 2.54 centimeters over 1 inch, all right? So basically, you can use either this conversion factor or this conversion factor to express the relationship between the inch unit and the centimeter unit. Now, which one you use is dependent on the type of conversion that you're trying to achieve. If you want to convert from centimeters to inches, then you would use this conversion factor. If you want to do the opposite, convert from centimeters to inches, or from inches to centimeters, I'm sorry, then you would use this conversion factor, all right? So it all depends on what you're trying to achieve. Let me just say here at this juncture, and that is that when you're using these relationships, again, you have to be careful about whether or not you're talking about exact or measured values. Now, by definition, 1 inch is equal to 2.54 centimeters. So this relationship is an exact relationship, all right? So let me just write right here. This is an exact relationship, right? So what that means, therefore, is that when you're doing any calculations, you're going to assume that the 1 here and the 2.5 here has an infinite number of sig figs, infinite number of sig figs, all right? So whenever you have a conversion factor which represents an exact relationship, then you know that it has an infinite number of sig figs, and you take that into account when you're rounding off. Now, let me just say this. Apart from that, all other relationships where you're going from, let me do this here, you're going from metric to non-metric or vice versa, right? Those relationships are considered to be non-exact or measured, all right? So what I'm talking about here is, for example, the relationship between the gram unit and the ounce unit given here, right? This would not be exact, so this would be inexact, all right? Same thing for this relationship. In fact, all of these three here are measured or inexact relationship, right? So inexact here, and this is inexact, right? The same is true for the relationship between the meter unit and the inch unit, the kilometer unit and the mile unit. Any relationship between metric and non-metric units will not be exact, all right? Now, the only exception to that, of course, is what I mentioned before, the relationship between the inch unit and centimeter unit. That is by definition, and therefore that would be an exact relationship. Now, if you have a relationship between metric to metric, or non-metric to metric, non-metric to non-metric, non-metric, then these relationships are exact, all right? So please keep in mind that as well when you're doing any calculations. If you're going from metric to non-metric or vice versa, then that relationship is non-exact, and you have to take that into account when you're rounding off. If you're going from metric to metric or non-metric to non-metric, in other words, if you're going from one unit in the same system as the other unit you're converting to, then that relationship is exact, which means that all the numbers involved will have an infinite number of sig figs, and you have to take that into account as well when you are doing any calculations or mathematical operations. All right, so just to give you two examples of how we do this unit conversion thing, here's a question. How many centimeters are in 26 inches? All right, how many centimeters are in 26 inches? All right, so the way we set this up is that we start off with the 26 inches first, because that's the information they're given. And you have to ask yourself, what do you multiply that by in order to convert from inches to centimeters? Now, we already know that from the previous slide, we already know that 1 inch, do this up here, 1 inch is equal to 2.54 centimeters, right? So this begs the question, what would go up here as a numerator and what would go down here as a denominator? And since you have the inch unit here and you want to cancel it, then the 1 inch would appear down here, right? The inch unit would appear down here, while the centimeters would appear top, so that these units will cancel out each other, and therefore you'll be left with the centimeter unit. So the only other thing we need to add to this is to put the numbers in their right place, right? So we put the 2.54 centimeters above and the 1 inch below. And then, as I said before, the inch units will cancel out, and then you do your number crunching on your calculator and you round off appropriately. And you'll notice that this here, let me write this here, is a measured value, right? While this here is an exact representation or exact value represented here. So therefore this has 2 sig figs and this has an infinite number of sig figs. So therefore what that means is that you have to round off your final answer to 2 sig figs, which in this case would be 66 centimeters. All right? Any questions about this? Any questions? Okay. So that's one example. So here's another example. In this case, you're given, you know what, let me erase the scribblings I had here to avoid confusion. Okay. All right, so let's look at this example. You're given 1.25 feet and you have to find the equivalent value in millimeters. So in this case, it's not as simple as the previous one because in the previous example, we only needed one conversion factor. In this example, you need to use actually a series of conversion factors to go from feet to millimeters because one would not expect you to find any direct relationship in any handout like the one I provided between the feet unit and the millimeter unit, right? So in this case, what they did was that they converted first the feet to millimeters, the feet to inches, and we all know the relationship between the foot unit and the inch unit, 12 inches equal 1 foot. And then we go from inches to meters, this relationship can be found in the handout. And then we go from meters to millimeters. And then of course we do the unit cancellation and you do your mathematical operation. And you'll notice that this is rounded off to 3 sig figs, right? And the reason why is because you have 3 sig figs here. It's a measured number. This is exact, so that has an infinite number of sig figs. This is not exact, so therefore the 1 here would be considered to be exact. Whenever you have a 1 appearing in such relationships between units, you consider the 1 to be exact, but this number here would not be exact. So this is 4 sig figs. And this here is exact totally, right? So therefore, when you round off your final answer, you have to round off to 3 sig figs here. So that's why this is expressed to 3 sig figs in this case, all right? So that's another example, a bit more complicated than the first one, but the same underlying principle applies, all right? Basically, you have to use, in this case, a series of conversion factors. You have to make sure that you set them up such that the unit that you're trying to get rid of will cancel out, and it will introduce the unit that you're working towards until you get to the final unit and your final answer, all right? Okay, any questions about this example?
Yes.
Yes, sir.
So you would do 1.25 times 12, then 12 times 39.37.
No, 12 divided by 39.37 because it's the 39.37 is the denominator here. So,
okay,
after you do the first one, then you divide by 39.37, right?
And then you're going to multiply again.
By 1,000, exactly.
Okay. Okay.
All right. Okay, any other questions, folks? Any other questions? Okay, so let's talk about an example of what I like to call a combined unit situation, right? So I'm quite sure we all know what density is, or what the term density means, right? Density is one of those physical properties, one of those quantitative physical properties for different substances. And by definition, density is a mass per unit volume, all right? And mathematically speaking, you can express it this way. Density is equal to mass divided by volume. And because density can be expressed this way, the units of density can be expressed as some unit of mass divided by some unit of volume. So the common units of density would be grams per cm cube or grams per mil. And by the way, these two are basically the same because the centimeter cube unit is the same thing as the milliliter unit. Another way of commonly expressing the density unit would be grams per liter, all right? Now, which one you use is dependent on the state of the substance. Typically, we use grams per cm cube or grams per mil when it comes to expressing the density of solids and liquids, all right? We use grams per liter when we are expressing the densities of gases. And the reason is kind of obvious. Gases basically have very low densities because for the same mass, they occupy a larger volume. So therefore, numerically speaking, it's more convenient to express the units of densities of gases in terms of grams per liter. And in terms of solids and liquids, we stick to grams per cm cube or grams per mil, all right? So the units in each case is a combination of two separate SI units, all right? And this is not the only example of this. You'll see this happening a whole lot when it comes to expressing the units of various quantities. Now, the thing about, oh, and by the way, this here is just a short list of different substances and their units. Water has a density of about 1 grams per mil, but as you can see, it changes with volume, which is true for most substances. If you increase the temperature of a substance, generally speaking, the volume would increase. So we have solids here, we have liquids here, and we have gases here. And as I said before, in the case of gases, the density units are usually expressed in grams per liter, all right? While the densities of liquids and solids are expressed in grams per mil or grams per cm cube. What you'll find typically is that metals tend to have high densities, right? So as you can see here, aluminum is about 2.7 grams per mil, gold is about 19.3 grams per mil, iron is 7.784 grams per mil. And then as you can see down here, liquids tend to be somewhat intermediate. Now mercury is a bit unusual because mercury is the only metal that exists under normal conditions as a liquid. So as you can see here, the density of mercury is very high compared to the other liquids in this list. And then we have the gases, which of course, typically their densities are very low, so low that their units are normally expressed in grams per milliliter. I'm sorry, grams per liters, all right? So that's basically just some examples of different substances and their densities. Now, because the density unit is a combination of a unit of mass and unit of volume, then we can also express the density as a conversion factor, all right? So for example, in the case of copper, the density can be expressed as 8.94 grams divided by 1 centimeter cube, all right? Or, let me write it here, you can express it as 1 cm cube over 8.94 grams, all right? So again, it depends on what you're trying to accomplish, which would require using either this one or this one, all right? Another thing you need to keep in mind is that because this unit is the result of two measurements, that means that this number here is a measured number, so to speak, even though it's a calculated number, but it's calculated from two measured values. So therefore, this number will have a finite number of significant figures. So in this case here, we have 3 significant figures represented here, all right? And that is true for all density values. So when you're using density values or any values that are the result of dividing or multiplying two measured values, then the resulting number will have a finite number of significant figures, all right? So that's something, again, you need to keep in mind when you're doing your work. Okay, so that's basically it for this chapter. So if there are no questions concerning what we have just covered, I'm just simply going to move on to chapter 2. So are there any questions? Any questions? Well, tell you what, before we move on to chapter 2, let me just do 1 or 2 quick examples concerning density. So let me remove this here. Okay, so simple example. What is the volume of 3.7 grams of copper, all right? So the conversion factor method is a method that one would use. So we start off with a 3.7 grams. So the question is, what do we multiply that by? And that would be the density. Remember we said that the density of copper is equal to 8.94 grams per cm cube. So we're going to put 1 cm cube above and 8.94 grams below. We do the calculations, and let me do this calculation here. 3.7 divided by 8.94. According to my calculation, this works out to be 0.4138 and some other digits, but we need to round off to two sig figs because we have two sig figs here. And we have three sig figs here. So therefore, the answer, according to my calculator, would be 4.1. And the units here would be centimeters cubed. So that's basically how you do that. So that's a simple example. I just thought I should show you how to do that. Okay. All right, let me move from this to chapter 2. Let me go here. All right. So in chapter 2, again, this is a bit of a review. A lot of what we're going to cover here in this chapter you would have met before. So we'll be covering the concepts of atoms, molecules, and ions, and other related topics, all right? So the first thing we want to talk about are some laws, basic law, fundamental laws in chemistry when it comes to the composition of compounds. And the first law we're going to talk about here is that of the conservation of mass. So this law says the total mass remains constant during a chemical reaction, all right? So that's one way of wording it. In different textbooks, they have it worded in different ways. You might see something like, in a chemical reaction, the matter is not created nor destroyed in a chemical reaction, but converted from one form to another, all right? And you might see it worded in some other ways in different textbooks, right? So basically what they're saying is that whatever the total mass of the products of the reaction that you end up with, that will be equal to the total mass of the reactants that you started off with, all right? So the example that is cited here is the example of the decomposition of mercury 2 oxide. So let me just write down the equation for that reaction. Mercury 2 oxide is a solid. When heated, it forms mercury and oxygen. And to balance this equation, you're going to need a 2 here, you're going to need a 2 here, right? So basically, whatever the total mass of the products that you get here, right, that will be equal to the total mass of the reactant that you started off with here, right? So that's basically what this law is saying, right? So basically, in a chemical reaction, matter is not created nor destroyed. That's basically what it comes down to. All right, so that's, oh, the equation is there already. Okay, anyway, let me move on to the next law, the law of definite proportions. And basically what this law says is that any pure compound will have the same composition by mass, all right? So it doesn't matter what the compound is, as long as it's the same compound, it doesn't matter where you get the compound from, the percentage of each element present in that compound by mass will be constant. So just to use a simple example of water, right? Water, as we all know, is made up of oxygen and hydrogen. So water contains approximately 89% oxygen and 11% hydrogen, right? Now, it doesn't matter where you get the water from. It doesn't matter if you get the water from a river, or if it comes from the tap, or if it comes from the sea, or if it comes from rain, or if it comes from outer space, it doesn't matter, right? Water is still 89% oxygen and 11% hydrogen, right? If you get a compound that contains hydrogen and oxygen, and it doesn't have these percentages, then you can rest assured that that substance is not water, all right? So that's basically what this law is saying. Basically, for any substance, the composition is constant, all right? Then we have this law, which is a bit wordy, the law of multiple proportions. And this law says, when two or more different compounds of the same two elements are compared, the masses of one element that combine with a fixed mass of the second element are in the ratio of small whole numbers, all right? So let me try to explain what this law is saying by using this example right here. So there are two compounds that can be formed when oxygen combines with carbon. You have carbon monoxide and carbon dioxide, all right? Now let's say that you have two samples of, well, you have one sample each of these two compounds, right? And let's say in one sample, you have 3 grams of carbon. In the other sample, you have the same mass of carbon. If you were to look at the masses of the oxygen combined in each case, you're going to see that you have 4 grams of oxygen here and 8 grams of oxygen here, right? Now, if you look at the total mass of each compound, in each case would be 7 grams of carbon monoxide and 11 grams of carbon dioxide. Now, if you look at the oxygen to carbon ratio in each case, all you have to do is divide the mass of the carbon, the mass of the oxygen by the mass of the carbon. That is what is done here, and that is what is done here. And then if you divide this ratio, this mass ratio by this mass ratio, what you end up with is a 2-to-1 ratio which basically represents the ratio of oxygens present in each compound, right? So that's what this law of multiple proportions is saying. It's saying that if you take the mass of one element in each compound, in this case, carbon dioxide and carbon monoxide in each case, if you take 3 grams of carbon in each of these compounds, and you compare the masses of the other element that is combined with the carbon in each case, you see that it's a small whole number ratio, in this case 2 to 1. And that should come as no surprise because, of course, in the formula of carbon dioxide, we have a subscript here of 2 for the oxygen, whereas we have a subscript of 1 here for the oxygen in the case of carbon monoxide, right? So that's basically what this law is saying. Basically, if you keep the mass of one element fixed between compounds that have the same elements, then the ratio of the other elements in terms of their mass would be a small whole number ratio, 2 to 1, 1 to 2, 3 to 4, 1 to 1, etc. All right? Okay, so that's the law of multiple proportions. And then we have, well, not a law, but a theory, right? The atomic theory of matter, all right? So this theory was put forward first by an English school teacher by the name of Dalton. And he came up with this theory based on what was known then about substances, all right? And this was a very important step in order for us to understand the nature of the atom. So according to Dalton, all matter is composed of extremely small indivisible particles called atoms, all right? Now let me stick a pin here before I move on to the other conceptual assumptions about this theory. We now know that this is not true, right? Back then, it was believed that the atoms cannot be divided. You cannot break it down into anything simpler. But now we know that not to be the case. We now know, and we're going to get into this later on, we now know that atoms can actually be divided into further, more fundamental particles, right? And of course, you know the different fundamental particles. You have the protons, you have the electrons, and you have the neutrons, all right? So this is an example of how science works. Somebody comes up with a theory, and the theory might be accepted for quite a while, and then other people come up with experiments and data from experiments which may contradict the theory, and therefore we do not accept or we have to modify the theory, all right? So that's basically what I wanted to say about this first assumption. The second assumption of the atomic theory of matter is that all atoms of a given element are alike in mass and other properties, but atoms of one element differ from the other atoms of other elements. So basically what this is saying is that if you could see two atoms, separate atoms of, let's say, oxygen, they would look exactly alike. They would have the same mass, they would have the same volume. There's no way you could tell the difference between them, all right? However, if you compare oxygen to sodium, for example, if you could actually see them, then you would see that they are the different mass, different size, etc. All right, so that's the second assumption of the theory. And then the third assumption here is that compounds are formed when atoms of different elements unite in fixed proportions. So, for example, you can have, in the case of water, hydrogen atoms combining with oxygen atoms to form water. And as we said before, the ratio in terms of their mass or their percentages would be fixed, all right? Then we have this assumption. A chemical reaction involves a rearrangement of atoms. No atoms are created, destroyed, or broken apart in a chemical reaction, all right? So that's basically what this is saying. And this actually explains what we said before in terms of the conservation of mass law. If you remember, we said that the conservation of mass law says that atoms or matter cannot be created or destroyed in a chemical process or chemical reaction. And the reason why that is so is explained by this particular assumption in the atomic theory, that basically when you have a chemical reaction, you do not have the destruction or creation of atoms. In fact, you don't even have the atoms breaking apart in a chemical reaction. Instead, what you have are rearrangements where you have bond breaking and bond making taking place and new substances are created. And we're going to get into all of that in greater detail later on, all right? Okay, so just to illustrate the atomic theory, let's say that we can actually monitor a chemical reaction between hydrogen fluoride and fluorine. The equation for this reaction I'm going to write up here. So it will be 2HF to form, I'm sorry, it's going to be H2 plus F2 to form 2HF. All right, so that's the equation for the reaction. So in this particular case, we have 3 molecules of fluorine. Now remember, fluorine is a diatomic molecule. In other words, each molecule consists of 2 atoms, all right? So we have 3 molecules of fluorine. We have 3 molecules of hydrogen, which are themselves diatomic, right? So we have 2 molecules here, 3 molecules here, but you'll notice it's a 1-to-1 ratio between the hydrogen and the fluorine, right? So what's going to happen? Each of these molecules here of hydrogen will react with 2 molecules of fluorine. So this hydrogen molecule will react with this hydrogen molecule will react with this, right? So therefore there'll be 1 fluorine molecule left unreacted. So when these 2 molecules of hydrogen fluoride react with these 2 molecules of fluorine, you're going to end up with 4 molecules of hydrogen fluoride, all right? So this is, you know, an illustration of the atomic theory, right? And note that this particular example obeys the conservation of mass law as well as the laws of constant composition. And also it obeys the, or it is explained by the atomic theory, all right? Basically, the atomic theory says that, you know, the same number of atoms of each element here on the left side will be equal to the same number of atoms of each element on the right side, all right? Okay, so that's just an example just to illustrate the atomic theory. Okay, so as I mentioned before, there are some subatomic particles that exist, we know now. So we have the protons and neutrons, which are located in the center of the atom, which is called the nucleus. And then we have the electrons, which are spread out and dispersed around the nucleus. And so these are the 3 fundamental particles that exist in every atom, excepting hydrogen, excepting the hydrogen atom or the normal hydrogen atom. So this table here basically shows you the different particles, as I mentioned before, and some properties that they display. So basically, these are the common symbols that we use to differentiate between the particles. This is giving you the relative mass of each of these particles. So what you'll find is that the proton and neutron are basically of the same mass, but the electron is much lighter, right? Significantly. And then in terms of the charges, the proton has a plus charge, the neutron is neutral, no charge, and electrons have a negative charge, and the location of the different particles in the atom are indicated to the right of this table. All right, so that's basically covering the basic nature of these particles. Another term that you should have met before, isotopes. These are atoms having the same number of protons, but different number of neutrons, right? And I mentioned hydrogen, normal hydrogen, which has no neutrons, but there are other isotopes of hydrogen, such as deuterium and tritium. The difference between them would be the number of neutrons, as you can see here, right? So hydrogen has 1 proton in each of these cases. All the isotopes have the same number of protons, but different numbers of neutrons. And what that basically tells you is that the isotopes are of the same element, right? The only difference between them is that they have different numbers of neutrons. So as such, these hydrogen isotopes behave chemically the same way. They're all identically the same way in terms of the chemical properties that they display. Now, they will display certain differences in their physical properties, which I won't get into. And those differences is due to the fact that they have different numbers of neutrons in their atomic structure, all right? Now, a typical symbolism that is used to represent the atomic number is Z, right? The letter Z, uppercase Z, which of course, by definition, as you should know by now, is the number of protons, right? So the number of protons is what is used to basically define the element. Every atom of the same element will have the same number of protons. So that's why we can say that these are basically the same element, but they're isotopes of each other, all right? Okay, so some other examples of isotopes, you have carbon-14, which has an atomic number of 6, so 6 protons, and therefore it has 8 neutrons. Chlorine-16, I'm sorry, chlorine-35. Oh, there's something I should have mentioned before, and I'm surprised that it's not here. Okay, so before I get into these here, let me talk about the mass number, right? I thought I had the mass number definition here. So the mass number here, and again, this is something you should know. The mass number, by definition, for an isotope is equal to the number of protons plus the number of neutrons. All right. So basically, and that is represented by the letter A. All right. So Z represents the atomic number, which is the number of protons, while A represents the number of protons plus the number of neutrons in the nucleus of an atom. So going back to these examples here, carbon 14, this 14 here is the mass number. The atomic number is 6. So since we know that the number of protons subtracted from the mass number will give you the number of neutrons, then 14 minus 6 will give you 8 neutrons, all right? Same thing applies here in the case of chlorine 35, which has 18 neutrons, and uranium 234, which is a radioactive element, which has 142 neutrons, right? So basically, if you want to find the number of neutrons, you take the difference between the mass number and the atomic number, and that's it. That's how you get the number of neutrons, all right? Okay, so that's as far as neutrons, protons, electrons, and isotopes are concerned. Now, one thing about isotopes is that for a particular element in nature, in the universe, what you'll find is that the relative proportion of a particular isotope is fairly constant, all right? So in other words, different elements or different isotopes will have what we call percent abundance, all right? So an example is given here of carbon 12 and carbon 13, right? So any sample of carbon that is present in the universe will have 98.892% of it being carbon 12, and carbon 13 would be 1.108%. And then there are some other isotopes. You have carbon 14, which is even less than the 1.108%. I don't remember exactly what it is, right? So we call these numbers percent abundance, and that can be expressed also as a fractional number, which is called a fractional abundance, right? Now, what I'm going to show you using this example is how we use this kind of data to determine what is called the weighted average atomic mass of, in this case, carbon. So let me get out of this here, and let me go to my sketch here. Okay, so according to the question here, in fact, let me do this. Let me see if I can copy and paste this, make life easier for me. Let's see if I can paste it here. Okay, success. All right. Let me bring this up here and then get rid of that. Okay, so basically you're given this data and you're asked to determine the relative atomic or the weighted average atomic mass of carbon based on this data. So the way we would calculate this is that for carbon 12, I would multiply the 0.98892 by the atomic mass of that carbon 12, which means I have to go back to this again. So the atomic mass of carbon 12 is 12 point and then 5 zeros after the decimal point. So let me go back to my sketch pad here. So 12.00000, right? And this would be AMU. And then I'll do a similar calculation for carbon 13. So for carbon 13, that would be 0.01108 multiplied by the atomic mass for carbon 13, which is 13.00335. So 13.00335 AMU, all right? So let me take my cheap but trusty calculator out and work this 0.98892 times 12.00000 equals, okay, so according to my calculation, I have to round this off to 5 sig figs. So this works out to be 11.867 AMU. And then I'll do the same thing down here, 0.01108 times 13.00335. And again, I have to round, well, in this case, I have to round off to 4 sig figs. So according to my calculation, this works out to be 0.1441 AMU. And then what I need to do next is add these two numbers. Now, when I'm adding these two numbers, I have to round off to the lowest number of decimal places, which means that I have to round off to 3 decimal places. So I'm going to add 11.867 plus 0.1441. And according to my calculations, this works out to be equal to 12.0, okay, 3 decimal places. So 12.011 AMU will be the final answer. All right. So this would be the weighted average. Let me write this down here. The weighted average atomic mass. All right. And you'll notice if you look at any periodic table, you'll see that that would be the second number associated with carbon in any legitimate periodic table. You have 2 numbers for each element given in a periodic table. You have the atomic number and you have the weighted average atomic mass. So all those weighted average atomic masses that you see for all the elements in the periodic table, this is the way they're determined, right? Once you know the percent abundance and the mass of each isotope, then this is the way you go about calculating the weighted average atomic mass, all right? Now, before I leave this, there's one thing I want to say to you, and this is oftentimes a source of confusion for students, and that is this. Please note that the weighted average atomic mass is not the same thing as the mass number, right? Students always, every semester that I've taught chemistry, students have always confused the two, all right? The weighted average atomic mass, or simply the average atomic mass, is not the same thing as the mass number. If you recall, we said that the mass number is the sum of the number of protons and neutrons present in an atom, all right, or an isotope, right? That's a mass number. The mass number is the sum of the number of protons and neutrons in an atom or isotope of an element. The weighted average atomic mass is simply the what we did here, the calculation that we did here, where you take the atomic mass of each isotope multiplied by its corresponding fractional abundance, and then you add all of those values up, and that will give you the weighted average atomic mass. And this represents the average weight of the atom of that particular element, taking into account the percent abundance, all right? So it's very important that you understand the difference between those two, all right? The mass number is the sum of the number of protons and neutrons, while the atomic mass is the mass of the atom, the average mass of the atom, taking into account the percent abundance of each isotope of that particular element. Okay, so much for that. Any questions? Okay, so let's continue our discussion. Okay, so some more things to say about the atomic mass. Let's talk about the definition of the AMU unit, right? 1 atomic mass unit is defined as exactly 1/12 the mass of a carbon-12 atom, right? So basically what this is saying is that the mass, by definition, the mass of a C12 atom is equal to 12 AMU exactly, all right? And therefore, that is basically how the scale, the AMU scale is determined. And it is a useful scale because we use it to express the masses of very small particles like atoms, molecules, ions, protons, neutrons, etc. Now, in terms of the relationship between the AMU unit and the gram unit, that's a relationship right here. 1 AMU is equal to 1.66 times 10 to the minus 24 grams. Now, for our purposes, we'll just round off that value to 1.66, right? So that would basically be the mass equivalent in grams to 1 atomic mass unit. And as I said before, the atomic mass of an element is the weighted average of the masses of the naturally occurring isotopes of that element. So that's what I was stressing before from the previous slide. All right, and please do not confuse it again with the mass number of an element. Okay, so I think this is going to be the last topic we're going to talk about here in today's class, the periodic table. We're all familiar with the periodic table. I don't know if you know about the history of it, but basically this guy that you see here, his name was Mendeleev. Let me write his name here. And you'll see different types of spellings of his name because he was Russian. So therefore, you know, to transliterate from Russian to English, as you can imagine, is a bit of a challenge. So you'll see various ways of spelling his name. Anyway, he was a chemist. I don't remember exactly the time frame when he was around. But one account I've read of how he came up with the periodic table was that he was writing a textbook about the known elements or the elements that were known in his day. And somehow he noticed that if you arrange the elements according to their atomic masses, which was the only thing that was known about elements in those days. They didn't know anything about atomic numbers. They didn't know anything about protons and neutrons and all of that. The only thing that they could use to basically identify each element was their atomic masses. So that's what he had to work with. So he arranged the elements according to their increasing atomic masses. And he found out that after so many elements, certain properties start to repeat themselves, all right? So he kind of put aside the task of writing the textbook and he formulated this table where all the elements displaying the same properties are placed in columns, but you still have in the rows the elements ordered according to their atomic masses, right? And so the elements that are in the same columns, they're called groups, right? And later on, it was discovered why, and we're going to talk about that later on, because it has to do with how the electrons are arranged in the atom, all right? Now, one interesting thing about the table that Mendeleev came up with is that in his table, there were certain gaps that were in his table. And those gaps represent elements that were not yet discovered, right? So what Mendeleev could have done, or what he did actually, was that he made certain predictions about those elements, even though they were not discovered, but he made some predictions about their elements, specifically based on their positions in the periodic table, right? He made some, predictions about color, melting points, the type of compounds they form, and so on. And it turns out that his predictions were spot on in most of the cases, if not all the cases. There was one account I remember reading about germanium, right? Germanium was not known when Mendeleev came up with his periodic table, right? But he made certain predictions about that element. And then when that element was discovered and they compare the properties of that element to the properties that he predicted, I mean, the resemblance is, was uncanny, right? I mean, he accurately predicted the type of properties that germanium would exhibit, all right? So, and he did this without knowing anything about the atomic structure because that theory, the atomic theory, didn't come about until after he came up with the periodic table, all right? So, one have to credit Mendeleev for what he did because he came up with a way of organizing the elements, even though he did not understand the actual nature of the fundamental particles of these elements. Okay, so this is a periodic table. After, Mendeleev came up with his table, then other elements were discovered, some other elements has to be shifted to other positions and, that took place over the greater part of a century. And then we come up with our modern version of the periodic table, which is what we have here, all right? So this is the periodic table. We're all familiar with it. In most legitimate periodic tables, each element would have two numbers, as I said before, associated with it. The lower number would be the atomic number, and the higher number would be the atomic mass, the weighted average atomic mass. Again, let me emphasize, this is not the mass number, it's the atomic mass, all right? Now, there are different ways of categorizing the elements. One way is shown here. If you look at this color scheme here, you'll see that the elements here can be categorized between metals and non-metals. And then there's a third minority groups known as semi-metals or metalloids, all right? So as you can see, the vast majority of elements in the periodic table are metals, all right? And then you have the non-metals, which are to the right of the periodic table. In fact, there's a thick line here, which you'd see in most periodic tables. That basically represents a line of demarcation between metals and non-metals, all right? However, you have some other elements which are known as metalloids, as I said before, and they basically would lie on one or the other side of that line, all right? So silicon, germanium, arsenic, antimony, tellurium, and astatine. I'm not sure polonium would be a metalloid, all right? So the two main classes are metals and non-metals, and the metals would be to the left, as I said before, excepting hydrogen. Hydrogen is unique, and we're going to see the reason why later in terms of the atomic structure, because one could make an argument that hydrogen actually belongs here, but also hydrogen belongs here based on its atomic structure. We're going to see why that is, all right? But with the exception of hydrogen, all the elements that lie to the left, or most of the elements that lie to the left are the metals, and then those that lie to the right of that line would be the non-metals, all right? And then, as I said before, you have some elements known as metalloids, which are basically located on exactly on one side or the other of that line. They're called metalloids because they have certain characteristics in common with metals, and then other characteristics in common with non-metals, all right? So that's why they're called metalloids. Okay, I think I'm going to stop here for today. So if there are no questions, or let me ask, are there any questions? Any questions?
No.
No? Okay, so that's basically it for today. So enjoy the rest of your weekend, and we're going to meet here next Tuesday, all right?